Right, dear students. So, regarding this applied, we know that we have to know what an isoelectric point. Basically, an isoelectric point, and we have the same number of positive and negative charges. So net charge will be zero. For example, this is the Victorionic form. Also, this is isoelectric point. Take a look at the number of negatives and positives. So three negative and three positive. So overall charge should be zero for isoelectric points. But for cationic form, we have to know that pH is less, but in anionic form, which means the pH is more than isoelectric point. Also, before talking about the structure of proteins, you have to know what we should know regarding the hydrolysis or condensation reaction. Is that, for example, if it is 50, if it is 40 grams, this is just an arbitrary numbers. So they are not molar masses. So what will be overall, the products are 90. So reactants will be 90 grams to, let's say 18 grams is the molar mass, 18. It will be 72. So always remember that for and or let me write in here to make it more clear. Let me write A plus A. We are getting A plus water. Imagine we have two amino acids. By the way, this is called dipeptide, but we have one amide bond and one water. Imagine the mass of this peptide bond is 50, in this amino acids 50-50. So overall reactant is 100 grams. We already know the molar mass of water, it is 18. So what will be the molar mass of this dipeptide? It will be 100 minus 18. It will be 72 grams. Okay. Also, don't mix molar masses with given masses. For example, let's say in this example, I use the molar masses. If it's a given mass example, as you have done in the CPA, you have to make sure right in here on the given methods. All right, so this was about the amino acids. We have to know the structure of proteins, what we should know regarding the structure of proteins. We have to know that we have four structure, primary, secondary, tertiary, and quaternary. Primary is easy, it's just a sequence of amino acids joined together by peptide linkage. So for primary, it's only the peptide linkage. And we already know the peptide linkage. Yes, peptide linkage is this linkage between two amino acids. So this is secondary structure. We have two types of secondary structure. And secondary structure is formed through intramolecular hydrogen bonds. This is intramolecular hydrogen bondings. Basically, we have two types of these, alpha helix. You have to know alpha helix and beta helical sheets. In both of them, we see there is an hydrogen bonding. So because of this hydrogen bonding, the primary structure folds and creates a secondary structure. And also remember what was hydrogen bonding. Hydrogen bonding, we need to have uh, either fluorine, oxygen, or nitrogen in one molecule inside intramolecular, and it should include molecular attached to again either fluorine, oxygen, or nitrogen. Take a look. We have hydrogen bonding in here in one amino acid. In another amino acid, it's connected to nitrogen. So we have condition number 2, and it is intramolecularly connected to why intra because it's the same amino acid structure protein to another oxygen, and condition number 3 is net. Okay, as you can see, the hydrogen bondings in secondary structure is between the amide bonds. You see, this is amide bond, this is amide bond, this is NH and CO, CO and NH. We see all of them are between amide linkage. Tertiary structure. So once we created a secondary structure, we have more bonding. This is called in tertiary structure. So we know that in amino acids, let me draw the backbone of amino acids. So this is the backbone of all amino acids. Also, we have a side chain. This is a side chain. We know that we have different amino acids. They have different side chains. And tertiary structures is because of this type of chain. Don't forget that. We have different kinds of tertiary structures. We can have, for example, hydrogen bonding, and then weak hydrophobic interaction, disulfide bonding, or ionic bonding between side chains, which further folds change the structure of the protein. Yeah, and lastly, the quaternary structure. Quaternary structure basically, again, they are connected by van der Waals forces. This is also called hydrophobic interaction. We usually have an extra component for quaternary structure. Also, quaternary structure is the combination of three or four or more different tertiary structure together. Also, we have an extra component, for example, hemoglobin. We know that in hemoglobin, we have an iron extra component, and this is an quaternary structure. Denaturation is the breaking, the destroying the structure of the secondary or tertiary structures. And once we do denaturation, we are creating the primary structure. And that's the biological activity of the protein loss because of this denaturation. It's because of heavy metal ions or organic solvents, and mainly in pH and temperature, it's changing. The activity of the proteins are changing. So these are the types of structure enzymes. Enzymes, they are biological catalysts. You have to know, you already know it from biology. We have an active site, and basically, this graph shows how the enzyme works, and we have an optimum temperature as pH for the enzymes, effect of enzymes on or effect of pH and temperature on the activity of critical enzyme. You see optimal pH for enzymes activity is around 7, and optimal temperature it's in this area. But after we have this, we are creating and evaporating. Okay, this is about biochemistry. I will also be uploading the YouTube videos. Please go through these YouTube videos.